Okay, welcome. Let's look at past questions. This is for River State University, Port Harcourt. So let's look at past question 2018-2019. I'll be doing more of the calculational part of this. So although there are theoretical parts, so you can look that after. Question number 1B. Question 1B. 1 kilogram of a fluid is compressed reversibly according to the law PV equals 0.3, where P is in bar and V is in meter cube per kilogram. If the final volume is 4 times the initial volume, calculate the work done on the fluid and sketch the process on a PV diagram. Okay, let's go down. Question number 1B, right? Okay, first thing first, a law was given. And the law states that PV equals 0.3, right? Yes. Next up, we know that what was given was the volume. They said that the volume V1 is equal. Okay, from this, we know that P equals, making P subject of formula, we have that P equals 0.3 all divided by V. Right? I recall that while teaching work, I said we should always solve our pressure in Pascal, but right here it is in bars. So how do we convert to Pascal? We multiply by what? 10 raised to power 5 Pascal. Okay, so this is it. Now recall that work done equal the integral P dV, right? Okay, so what do we do next? We substitute the value of P into this equation. We know that work done equals the integral V1 V2 P is equal to 0.3 V times 10 raised to power 5. So I'm substituting this into this. Therefore, I have 0.3 times 10 raised to power 5 all divided by V, dV. In integrating this, I'm integrating with respect to V. So every other thing that isn't V is a constant. So we have to bring this out of the integral sign, and I have that 0.3 times 10 raised to power 5 integral 1 over V dV. Okay, what is left here when I remove this? 1 over V. This is it, right? So let's integrate that. I have that 0.3 times 10 raised to power 5 gives us the integral dV over V. So integrating, we know that integrating 1 over A gives us ln A, right? Same thing applies there. Integrating 1 over V with respect to dV gives us ln V. So therefore, we have that this equals 0.3 times 10 raised to power 5 ln V. And we have a limit V1 to V2. V1, V2, right? Okay, and this gives us a 0.3 times 10 raised to power 5 gives us ln, okay, ln. Now, since there's a limit, we say the upper limit minus the lower limit. So this gives us V2 minus V1, right? Therefore, we have that W equals 0.3 times 10 raised to power 5 ln. Now, from our law of indices, if we have this ln V2 minus V1, it is the same thing as saying ln V2 all divided by V1 from our law of indices, from the law of indices. Okay, next up, recall but from our question, it was stated that the final volume is 4 times the initial volume. That is, V2 is equal to 4 times the initial volume, 4 times V1, which is the initial volume. Therefore, since V2 is equal to 4 times V1, we have that W equal 0.3 times 10 raised to power 5 ln 4V1 all divided by V1. Therefore, V1 can cancel out and we have that 0.3 times 10 raised to power 5 ln 4 over 1, which is what? Ln 4. So what is ln 4? Using our calculator, we have that ln 4 gives us ln 4. This gives us 0.3 times 10 raised to power 5 ln 4 gives us 1.3863. Okay, so multiplying this, we have that our work done equals 0.4159 times 10 raised to power 5 joules. So we can convert these to kilojoules. Therefore, we have that our work done equals 1.59 kilojoules. Okay, I hope you still know how to convert to kilojoules. This is it. We have 10 raised to power 5, right? And kilo is what? 10 raised to power 3. Therefore, we have 10 raised to power 3 times 10 raised to power 2, right? Now, multiplying this by this, we have 41.59 times 10 raised to power 3. And 10 raised to power 3 is known as kilo, so it gives us 41.59 kilojoules. Next up, we are asked to calculate, we are asked to sketch the process, and sketch. So let's sketch the process. Let's sketch that. This will be done on a PV diagram. This will be done on a PV diagram. So this gives us a p-axis. The horizontal gives us a p-axis. Sorry, the vertical gives us a p-axis and the horizontal gives us a v-axis. So let's look at this. Looking at this, we know that P is inversely proportional to V. This is what I mean. P is inversely proportional to V. That is, P is equal to a constant over V, which is this. So this becomes a constant over V. Therefore, an increase in P leads to what? A decrease in volume. Also, an increase in volume leads to what? A decrease in P. Okay, let's look at that. So if I have P1 here, this is a decrease, right? From the origin, 0, and this P1. Therefore, P2 is greater than P1, right? So if there is a decrease in pressure, there should be what? An increase in volume. Therefore, if we have P1, our V1 should be B, should be on an increase. Therefore, P1 equal V1. Also, if there is an increase in P, which is P2 to P2, then there should be what? A decrease in V, which is what? V2. So let's match that. Let's match that. So an increase in P2 leads to what? In P leads to a decrease in volume. Therefore, P2 equal a decrease in V, which is what? V2. Therefore, let's trace that. Let's trace that. So we have that this right? Yeah. Okay, let's trace this too. A decrease in pressure leads to what? An increase in volume. Therefore, we have tracing that we get this, right? So let's connect these 2 points. We can't use straight line to connect these 2 points since the law given was not or is not a straight line equation. This is not the law for a straight line equation. Therefore, this should be a parabola. That is, we should have a curvy line. It shouldn't be that straight. Okay, this isn't straight. It is a curve, a parabola. Okay, next. So this is the sketch of the process. So this answers our question 1B. Our work done is given as what? 41.59. Therefore, work done is done on the surrounding since it is positive. Also, this gives us the sketch of the process. Okay, question 2B. See from same past question. We have fluid with a specific enthalpy of 3450 kilojoules per kilogram enters a condenser at a rate of 5620 kilogram per hour and leaves with a specific enthalpy of 184 kilojoules per kilogram. If the enthalpy of the cooling water circulating through the condenser tubes increases at the rate of 172400 kilojoules per minute. Determine the rate at which heat flows to the atmosphere from the condenser. Okay, let's do that. First thing first, remember to list out your parameters. Okay, for a condenser, heat flows to the cooling water and the atmosphere. The heat flowing to the surrounding is known as the heat rejected. Okay, let's do that. So first and first, we list out our parameters given. Our initial enthalpy, the initial enthalpy that was given equals 3450 kilojoules per kilogram. Right? Next up, we are given the final enthalpy to be 184 kilojoules per kilogram. We are given a mass flow rate m dot to be 5620 kilogram per hour. And if you could recall, I will always say this, your mass flow rate should be in kilogram per second. So in converting this to kilogram per second, we just divide all through by 3600 seconds. So this gives us that our mass flow rate equals 5620 divided by 3600 seconds. Right? Since in an hour we have 3600 seconds. Therefore, our mass flow rate equals 1.56 kilogram per second. Next up, the heat from the fluid is given by the change of enthalpy as it moves from the entry to the exit of the condenser, and this can be represented as Q1 or Q dot 1 equals M dot H2 for a condenser minus H1, right? So we can get the heat which flows from the entry point to the exit of the condenser as Q1 equal to M dot multiplied by H2 minus H1. Your M dot is known as your mass flow rate. So therefore, we have that Q1 equals 1.56 in bracket. What is our H2? 184, right? Minus H1. H1 is given as 3550. So 3450 rather. Therefore, calculating this, we have that 1.56 multiplies minus 3266. Therefore Q1 equals minus 5094.96 kilowatts, right? Kilojoules per second. And I've said this over and over again that whenever you have joules per second, it's the same thing as saying watt, which is your power. So this gives us minus 5094.96. Okay, let's go on. The negative sign indicates that there's a heat rejected, right? There's a heat rejected by the fluid. Next up, we calculate for Q2. Okay, Q2 was given, and Q2 from the question was Q2 was given as 172,400 kilojoules per minute. Therefore, in converting to kilojoules per second, we have to divide through by 60 seconds. We know that 60 seconds make up a minute. Therefore, this gives us kilojoules per second, right? Therefore, we have that our Q2 equals 2873.33 kilowatts. So this is the heat gained by the cooling water. Our Q2 is the heat gained by the cooling water. Next, we should determine the rate at which heat flows from the condenser to the atmosphere. So in doing that, let's call that Q3. That is the heat loss to the atmosphere. So our Q3 becomes total heat rejected minus heat gained by the cooling water. Therefore, we have that Q3 equals, what is our total heat rejected? Our total heat rejected is given as Q1. Q1 minus the heat gained by the cooling water, which is what? Q2. So for this, we don't have to write minus 5094. We know that the negative sign there indicates that there is a heat rejected. Therefore, we have that Q1 equals 5094.96 minus the heat gained by the cooling water, which is 2873.33. And in subtracting this, we get that our heat loss to the atmosphere or surrounding Q3 equals 2225.63 kilowatts or kilojoules per second. Okay, this gives us the heat loss to the surrounding or atmosphere. This answers our question.